I'd like to do a short introduction. We are xSeriCon. We're a consultancy, safety consultancy. We specialize in safety studies and other safety-related activities, HAZOP, SIL, functional safety, alarm management, RAM studies, and more. My name's Dr. Joe Wiggers. I'm senior consultant here at xSeriCon. My background is as an industrial design engineer, chartered engineer. I've worked in the oil and gas and automotive industries, and more recently I've joined the safety industry. So I'm very pleased to see you. Thank you for joining us. I hope you'll find this webinar useful in understanding, getting an insight into failure rates, where they're used, how they are useful, how they are best used, and how they should be treated with caution as well. My colleague, Dr. Peter Clark, if you'd like to do an introduction.
Good morning, everybody. My name is Peter Clark. Apologize for the lack of webcam, but you can see how ugly I am anyway from the mugshot, so that should be enough to keep you awake at night. Thank you very much for joining our call today. I'm the Managing Director of xSeriCon, and I echo Joe's comments that we hope you find today's webinar useful, and we'd very much appreciate any questions or comments or feedback, and there'll be plenty of opportunity for that later on. Okay, I'll pass back to Joe.
Thank you, Peter. So, as I said before, we're going to be talking about understanding and sourcing hardware failure rates. And the first thing we should talk about is, well, what are failures? What is a failure? Well, failure is a very big topic, so we need to focus down and look at a more specific area. We're going to be focusing today on the chemical process industry. We're going to be looking at control and safety functions, and to be honest, mostly we'll be focusing on safety functions, and we'll be looking at physical failure of the equipment that performs those control and safety functions. So it may be mechanical, electronic, electrical equipment. In terms of types of failure, you can divide failure into two types: systematic failures and random failures. For the purposes of today, systematic failures can be considered as those that are caused by human error. Examples might be, let's say, wrong gasket material chosen, and when temperatures unexpectedly rise, gasket fails, you get failure. You might have a valve that's installed the wrong way around, or perhaps you have a holding vessel which normally works fine but is too small for simultaneous evacuation of two systems. So when you've got a specific combination of events occurring, the error comes to light and failure is guaranteed. Random failures are a lot harder to predict, especially to predict when they will happen. They might be occur due to different environmental stresses, and they often can't be related to a specific cause. Another way of looking at the difference between systematic failures and random failures is to consider how you treat them. Systematic failures, you should work towards preventing them. Whereas random failures, because it's so hard to tie them to specific causes, they need to be mitigated. And that's why we're going to be focusing today on random failures, because the approach you take for mitigating those failures is very different to those failures which can be prevented. So, moving on. Let's have a look at failure rates, and here is what is commonly known as the bathtub curve. It apparently looks like a bath. So if you imagine yourself lying with your head at the left-hand end and your feet on the right hand, you can see that it slightly resembles a bathtub. This is a curve depicting failure rate against time and service. It's not the failure rate of a single piece of hardware. Rather, it's the failure rate of a whole population of hardware. So if you imagine a particular valve has been manufactured and there's 10,000 of them out in service, and if you plot how many of them fail against their time in service, you will expect to see a curve which looks often, very, very often looks something like this. So we can divide the bathtub curve into three sections. You have your burn-in period. It's sometimes referred to as infant mortality. That's the point at which any weak items fail. So you start off with seeing higher failure rates early on in the time and service. Then you reach a point at which you have quite a low failure rate and relatively constant. It might be dropping slightly, but you can see that when we work with failure rates, we actually model it as a constant failure rate, shown by the green line there. And at some point, you come to the end of the service life of your piece of hardware. And you get to the wear out section. That's when the piece of hardware is subject to wear mechanisms, fatigue, failure, and so on. And you see a significant rise in the failure rate of those items. So the purpose, of course, is to use the item during its working life. So how do we fail? How do we express failure rate mathematically? You'll have seen this, the Greek symbol lambda in the previous slide. That's the letter that we use to represent random hardware failure rates. And we assume it to be constant over the device's lifetime. Its dimension is in failures per unit of time. Of course, failures don't have a unit, so it's per time. You might want to measure it in failures per year or per hour, but in safety systems particularly, and also in a lot of control systems, you would want far more reliable equipment. So another unit that's used is fit failure in time, and that's defined as one failure per billion hours. So that is approximately a failure every 100,000 years, I think, just over, a little bit over that. And you can have a look at some typical failure rates. Shutdown valve, for example, you might expect to see around about 400 fit. So that's a failure every 300 years. Safety relay is 2 orders of magnitude more reliable typically. So 3 fit you might expect to see. And a smart pressure transmitter is about 100 fit. So instead of every 300 years, you'd expect to see a failure every 75 years or so. Let's talk about failure modes for a little bit. So obviously with random failures, there's not a lot of point in talking about the cause, because we've defined random failures as those that it's hard to link them to the cause. But we can talk about them in terms of their effect. The most important effect that we want to look at are what are called dangerous failures. So a SIF, a safety instrumented function, that's a safety piece of equipment. A dangerous failure would be one in which, when it was required to act to bring a dangerous state into a safe state, it was unable to do so. Or if it's got redundancy, then you have loss of redundancy. So it's unable to, there may be another piece of equipment that can. But so here's an example. We have a spring return actuator. It's required to bring the process into a safe state. And if it's spring return, you would expect it to be in such a way that in most cases, the spring would bring it to that safe state. If the spring breaks, Then when you have loss of power and your actuator is unable to move under power, the broken spring is unable to move it into a safe state, and that would be a dangerous failure. A safe failure is also very much of interest, not from a safety point of view, because a safe failure would bring the process to a safe state when it wasn't required. So in the example given here, you might have a reduction in the pressure, which would cause the piston to be unable to counteract the spring return. The spring would bring it into a safe state. Why that's of interest is because that could interrupt the process and there would be economic consequences. You don't want to have your process constantly interrupted. And then there's a third one, just to complete the set. There's no effect failures. So there's some sort of failure on your piece of hardware which doesn't affect its ability to perform its function. So the example here is the position indicator is faulty. It doesn't perform exactly as it's designed to. Maintenance may find it difficult to perform checks because the position indicator is not correct, but when it's required to act, it's able to act, and so it's got no effect. Just quickly look at other failure measures than lambda, the failure rate. You might have come across mean time to failure, mean time between failure, or mean time to failure spurious. Mean time to failure, I actually gave examples of when I was talking about the lambda. I said, well, you know, a 400 fit would be 300 years between failures. Just to say, it's the inverse of the failure rate. It does not mean that the device will last for 300 years. It means rather than that if you have a population of devices, and let's take an example. Let's say we have 300 devices that all start the service at the same time. We're going to put the conditions on that they all of them will be replaced before or at the end of their useful life, and that any that break are repaired or replaced. You would expect to see out of those 300 devices, you would expect to see an average of about one of them failing every year. And that's the meaning of mean time to failure. That 300 years is a collective measure still. Mean time between failure just adds on the time it takes you to restore a failed device. So there's the repair or replacement, and there's the time taken to bring it back online. Now, if you have devices which are relatively unreliable, let's say you expect to see a breakage every few days, and it takes you 1 day to restore, then there's an important distinction. However, in most process control and safety applications, you expect to see much longer mean time to failure, so that mean time between failure is approximately equal to mean time to failure. There isn't a significant difference. And then mean time to fail spurious, again, we're interested with this in the economic consequences. That's sort of a measure of how often you would expect to see spurious interruptions of your process. So it's the inverse of lambda safe, the safe failure rate. You may have heard of this term, the B10. This came from the bearings industry and really only applies to frequently or continuously operated equipment. And it's a statistical measure of the mean time for 10% of a population of devices to fail. It is used in reliability applications, although as I understand it, it's more often used for things like determining warranty times warranty periods and so on. I haven't come across the use of B10 in safety applications, but I'm aware that they are talked about at times. It's important to understand the concept of mission time here because there's a common misconception. So let's first define mission time. You've heard me talking about the useful life. That's the bottom of the bathtub in the bathtub curve. It's the period of relatively constant failure rate. Mission time is the time that the engineers in a process determine they're going to leave a piece of equipment in before they repair or replace, refurbish the equipment. You can see here that it's quite obvious that the mission time should be less than or equal to the useful life of the piece of equipment. And obviously, because you're using a lot of different pieces of equipment, each of them has their own individual useful life. So if you were to wanting to maximize your mission time for each piece of equipment, you would have different mission times for a lot of different pieces of equipment. The reason it's important to understand this concept of mission time is because in projects that we've come across, a common confusion, a very common confusion, is to confuse the plant lifetime with mission time. And that's fine if you have a short plant lifetime. But if, as you would typically expect, you have a plant lifetime of maybe 30 years, a lot of the pieces of equipment will have a useful life that's shorter than 30 years. And that confusion means that there's no planning for replacement of those pieces of equipment when they are well into their wear out phase of their life, and therefore the failure rates that were used to calculate the reliability of the equipment are not valid. So we're beginning to look now at how we can use failure rates, and it's important to understand whether the failure rates that you see are reasonable. This is an example we've given here where you see two very, very different failure rates for two technologically extremely similar models of valve. So there are three ways of obtaining failure rate. We would say that the most valid way of doing so is to base it on actual field performance, statistically treated data for a valid amount of service hours would give you the failure rate, and preferably it'd be good if that was based on performance in broadly similar applications to the one that you're considering. Another approach is to do an FMEA, because when you have a product which is not has not been in service for long enough, doesn't have the millions of service hours required for the data for field performance, you could perform a failure modes and effects analysis. That's where you perform an analysis where you consider the components of the part, you consider the reliability of the components, you break down the failure into different causes, and it's a really extensive process for considering how the part might fail. Of course, it's not as good as field performance. And then finally, and often in support of FMEA, you might have cyclic testing. Cyclic testing is an accelerated testing method where you will repeatedly use the piece of equipment until it fails. Cyclic testing can be extremely useful, but we made the distinction just now before about the importance, when we were talking about the B10 value, the importance of continuously used equipment compared to equipment which isn't used very often. And the problem with cyclic testing is it only measures some of the failure modes. So, for example, you may have equipment that's subject to seizing, sometimes referred to as stiction. You might have cold welding, for example, of a valve that's been left in a particular position for a long time. Because, of course, your safety equipment, you want to preferably never have to be used. You want your process to be perfectly controlled for its entire plant lifetime. And you certainly don't expect safety equipment to be used very often. So there are failure mechanisms which cyclic testing, it's not just that it doesn't test those failure mechanisms, it actually actively prevents those failure mechanisms, such as seizing, plugging of lines possibly. And so you see here in the example, the Cameron BD series has a 29 fit, and that was assessed based on cyclic testing, whereas the Swagelok was based on field performance. And you can see there's a huge disconnect. 29 fit is a very optimistic value for a valve reliability, and it would give you a false sense of security about how reliable your piece of equipment was. Just to give an example of the importance of the frequency of use, I used to work with a test machine in which the designers had decided to use an emergency stop button for releasing the safety guards. It wasn't a good choice because we only used the test equipment for maybe 1 week in 4, and yet the safety button, the emergency stop button, had to be replaced around about twice a year. It's not designed for that frequency of use, and we should really have taken it back and asked for a redesign on it. So at this point, I'd like to hand over to my colleague, Peter.
Thank you very much, Joe. So we've heard there from Joe, who's very nicely covered a description of what failure rates mean and where they come from. So the next question is, well, how do we use them and why are they important? And I'd like to give you some examples of the types of application of random hardware failure rates that we typically encounter in our risk analysis studies. And I'm going to cover 4 out of the 5 methods that you see on your screen now. The one I'm going to skip, just in order to save a little bit of time, is the third one, failure modes and effects analysis, or FMEA. If you're interested in FMEA, then please let us know afterwards, because we're happy to share our knowledge on that, and we could even run a webinar on that if there is interest. Joe, can I have the next slide, please? First of all, LOPA. LOPA is a layer of protection analysis, which is becoming one of the most common methods for selecting the SIL target of a safety instrumented function. Now, SIL is a measure of the level of reliability required by a safety function, such as, let's say you've got a trip which operates on, let's say, high pressure or low level in a vessel to prevent some unwanted consequence. So you need to assess the level of reliability required from that function, which is expressed in terms of a SIL, for example, SIL 1, SIL 2, etc. And the lambda value, the random hardware failure rate of the individual elements within the safety function, is one of the key input values to that. Now, actually, I should correct myself. It's not the lambda value of the safety function. It's lambda values of the components that may fail, leading to a demand on the safety function. So because the LOPA analysis relies on knowing the frequency of the potential causes of upset that lead to a demand on the safety function. And those values can come from or those triggers can come from other pieces of equipment malfunctioning. So in the blue box, you can see, for example, you may have an emergency shutdown valve, which is supposed to be normally open, but if it malfunctions and closes, then it can lead to all kinds of knock-on effects, eventually leading to demand on a SIF. So in order to assess the frequency of that event, we need to sum up the lambda d values for the various components that can result in that ESDV failure, which might be potentially the valve itself, its actuator, a solenoid if it's a solenoid operated valve, the air supply to that valve, which if the air supply is lost, then it goes to its safe position and triggers this event. The logic solver that's controlling that valve. Maybe if that valve is being controlled by some other sensors, then the potential failure rates for those sensors as well. So all of those can be added up to come up with a predicted value for the frequency of that initiating event. Alternatively, if you've got plenty of statistical data from your field operational records, then you can use that statistical evidence to say, well, on average, we have seen this type of ESDV spuriously closing, let's say, one time in 30 years per valve. So then they would use that valve as that value as the lambda. The other thing that you need lambda for in LOPA is for the independent layers of protection, which means any other protective function or device that you've got that can also mitigate the consequence that you're trying to avoid. And that would be, for example, some kind of pressure relief valve or an independent control loop, maybe a check valve, maybe a separate trip function in the control system, maybe an alarm with an operator response. For all of those, if you're going to try to claim credit for them in the LOPA, then you need to have some justifiable value for how reliable they are. And that depends on the failure rates of the elements which are used to implement those layers of protection. Okay, Joe, can I have the next slide, please? So the next example of a technique that relies on lambda values as inputs is fault tree analysis, which is my personal favorite out of all the analytical techniques that we use these days. And just to give you a very simple example, supposing we are trying to estimate the frequency of the failure of lighting within a given area, let's say a public area such as a supermarket or a cinema, or maybe the emergency lighting in a operating chemical plant. And just to give an extremely simple example, the lighting can be supplied by a main power supply or by a battery backup system. And the lighting will fail if both of those power supplies are simultaneously unavailable. So the way we would analyze this in a fault tree is to treat the main power failure as the main source of power, the normal default source, and to use the lambda values for failure of the components of the power system, add them up in order to come up with a total frequency, predicted frequency for the power failure. For the battery backup system failure, we have to assess that as a probability of unavailability of the system. We can't handle that as a probability in fault tree analysis because since we're doing a logical AND operation on these two events, you can't AND two frequencies together. You have to AND a frequency and a probability. Otherwise, the units of measure don't work out correctly. So in order to assess or predict the probability that the battery system is unavailable at any given moment, which of course the moment of interest would be when the main power fails, one of the ways we can do that is simply to divide the mean time to restore, that's the repair time when it's faulty, by the mean time between failures, the MTBF. Those are values that Joe introduced to you to in one of the earlier slides. A typical ratio for those might be somewhere of the order of 0.01, 0.02, which means, let's say, unavailable 2% of the time. And that's the number that we would feed into the calculation of the fault tree. Joe, can I have the next slide, please? Another very important use of lambda values is in a technique known as SIL verification. A SIL verification is the task of calculating the predicted unavailability of a safety instrumented function. Which, if the function is very simple, we can do that simply by adding up the lambda values of the elements in the function, such as the sensors and the logic solver and the final elements, the shutdown valves or whatever we have that actually act on the process. But the calculation very quickly becomes complicated as soon as we start introducing factors such as proof testing and redundancy within the function. And at that point, it becomes too complicated to do a quick calculation on the back of an envelope or in an Excel spreadsheet. So that's when people typically turn to dedicated software for that purpose. What you can see on your screen at the moment is a screenshot from our own software offering, which is called Silability. And you can see the box on the left side where the lambda values of this particular component have been entered. The component in question is the Yokogawa pressure transmitter. So those lambda values have been obtained from some database or some other source of data, which I'll tell you about in a moment, and entered into the calculation there. If you want to know more about how SIL verification works and what's involved in it, we have another webinar that you can find the recording of on our YouTube channel, or you can simply contact us and we're happy to talk you through that. And the final technique that uses lambda values that I'd like to tell you about is RAM study. RAM is reliability, availability, maintainability study. And it's a very powerful technique that's used to predict the expected availability of a plant as a whole. And this is to see if we can meet a target that's set usually by management. So let's say, for example, we're operating some kind of critical utility or some plant where high availability of the plant is critically important, either for safety purposes or for economic reasons. Let's say we set a 98 or 97% availability or uptime for the plant as a whole. How can we assess whether we are actually likely to achieve that? Well, RAM study is the way to do that. And it relies on doing calculations which can be based on a method such as a reliability block diagram, which is, you can see a very simple example of on the screen now. The reliability block diagram is a simple model of the architecture of the system, showing how you might regard as information flow going from the left side to the right side. And as long as there is a path for information to flow from the left to the right, then the system works. But as soon as any component of the system fails, then it may block the flow of information, and then the system as a whole is failed. But as you can see, we have some places where it splits into two branches, two trains, providing redundancy. So if one train fails, the other one can still allow the information to flow from left to right. In order to calculate the availability of the overall system, we need to know the failure rates of each individual block in the diagram, and those values come from the dangerous and the safe failure rate, the lambda values. The example you can see on your screen is taken from a book of practice exam questions that we provide at xSeriCon. And if you want more details about that, you can find a page on our website dedicated to that. Okay. So much for what failure rates mean and why they're important and how to use them. Well, now the crunch question is, all right, now I know I need them, so where do I get them from? So we'd like to suggest some possible sources. First of all, there are databases available. Our own software for SIL verification and that of other providers sometimes comes with a built-in failure rate database, which you can search, and then you can transfer the values automatically into your calculation. And even if you're not actually using the software to do the calculations, if you require the lambda values for some other purpose, you can still extract the numbers from the database easily enough. So that's one source, and our own database has got more than 3,000 sets of data in it. Another option is to find freely available sources of data on the web. One of those is provided by Exeter. It's called the Safety Automation Equipment List, which you can find by searching their website. And that's quite a nice set of searchable equipment where you can search for the type or the name of equipment and find out if there's a SIL certificate or maybe an FMEA report provided there in that equipment list that allows you to obtain the lambda values. Another similar source produced by a different supplier, TUV, is known as Certipedia. Again, you can find that just by searching easily enough on the web. And if you don't find what you're looking for there, then you can also check the websites of individual equipment manufacturers, because sometimes they publish their own failure rate data, for example, in the form of a SIL certificate on their own website, and you can just download it immediately. Another option is to use paid-for resources such as repositories of failure rate data. Probably the most famous of these is the OREDA database, which stands for Offshore and Onshore Reliability Database, which comes from an industry consortium based around the oil and gas industry in Norway. It's very detailed, and it's based on, well, I should say it's very compendious. It covers a wide range, a very large number of items of equipment, and it's based on a huge amount of statistical data from field observations. The difficulty with using OREDA is that the data is not very fine-grained. So, for example, it may not distinguish very clearly between dangerous and safe failure rates or different kinds of failure modes. And then it relies on some interpretation on the user's part to know how to actually use those values in practice in a calculation. Another alternative source is provided by CCPS, which is the Center for Chemical Process Safety, and that is part of the American Institute of Chemical Engineering. And they've produced these two guidelines, which are in the form of published textbooks. They contain tables of failure rate data that you can purchase and use. Again, similar issues to the OREDA database in that the data is not always kind of sliced and diced in quite the way that you would optimally need for your calculations. And another potential concern with the CCPS is it's not always very transparent where the data actually comes from. And that would be a concern if you're trying to ensure compliance with the functional safety standards, such as IEC 61508 or 61511, because a requirement of those standards is for traceability of the data. So you need to have some evidence of where that data ultimately comes from. Some other alternatives, you can always contact the equipment manufacturer and ask them to provide their failure rate data, which may come in the form of a SIL certificate or a safety manual, or maybe some other kind of analysis report. Your success in getting information from the manufacturer may vary. Some are more kind of clued up to the need of the industry to provide this data than others, and some are more forthcoming in providing their data than others. But some of them, I would say, especially the smaller players in the industry, they understand this. They know that their users need that data, and they're fairly open and transparent with providing it. Another option is to try to find data for a similar device from another manufacturer. So let's say you're using maybe a ball valve as a shutdown valve from some less commonly known supplier. If you can't find data from that particular supplier, you could search one of the databases or other sources like the Exeter or TUV websites and find similar devices. Maybe look at 2 or 3 different trunnion mounted ball valves from other manufacturers and take an average, or take the worst case value that you see among those others. Because to be honest, for a simple mechanical piece of equipment, the amount of variation there's going to be in the design for equipment that is intended in a similar safety critical application is not honestly going to be that much. It's not going to be an order of magnitude difference from one manufacturer to another. So I think it's reasonably legitimate to take a value or take a range of values that you find for other similar devices and either take an average or take a worst case value from those. Another thing you can do, you can look at the user guide for our software Silability. The user guide you can obtain freely by downloading it from our website. And it's got quite a range of tips for how to find failure rates. And then finally, your kind of fallback option is just get in touch with us. We have some other data that we don't publish, but we can make available on request, and we can always provide some guidance and some tips, or we can show you how to do your own, for example, FMEA analysis to get those numbers if that's kind of your last resort. One possibility for obtaining lambda values is if you do have a lot of observations based on your own operations or maintenance data that you've accumulated over a number of years of careful record keeping, you might be able to use that to come up with a reasonable lambda value. And the way to do that would be to divide the number of failures that you've observed in practice +1 divided by the total number of accumulated hours that those devices have clocked up in service. Now, the reason for the +1 is because in practice, the number of failures you've observed is hopefully rather small. Could be potentially in single figures, like maybe only 3 or 4 failures. And if you only use the exact number of failures that you've observed, then you're assuming that the probability of failure since the last failure has been 0. In other words, you're calculating an over-optimistic failure rate. If you add 1 to that, then you're kind of assuming the worst case, which is the next device is just about to fail any minute now. So that gives you a slightly more conservative value for the failure rate. Now, the big caveat thing that you've got to watch out for this is to make sure that the result you come up with is statistically valid. And that's only going to be the case if you've got a very large number of operating hours of experience. And as a kind of rule of thumb, I would say the absolute minimum number of hours that you need to be looking at to evaluate a lambda value for a safety critical device is 10 million hours of experience. Now, just to put that in perspective, since there's roughly 10,000 hours in a year, if you've got a population of 1,000 devices that you've had in service for 1 year, that is 10 million hours of operating experience. Or maybe you've got 100 devices that you've been operating for 10 years. That also gives you 10 million hours. But you can see that that's quite a tall order. And that relies on having a lot of very high quality recording of data that's gone on over many years. So this is not something that many, especially smaller operating companies, will able to achieve. And especially with, should we say, less devices that you have fewer numbers of, like, for example, analyzers. You don't have 100 analyzers or 1,000 analyzers. You maybe have 3 or 4 analyzers in your plant. Whereas shutdown valves or pressure transmitters, maybe you do have 100 or several hundred of them. So it might be feasible for those more common devices. Well, that's all that we wanted to cover in our talk today. Just a quick kind of helicopter overview of lambda values, what they mean and how to use them and how to get them. The floor is open now to questions. If you'd like to ask a question now, please go ahead. You can either type it in the chat box or unmute your mic. Alternatively, send us an email afterwards and we'll be happy to get back in touch with you. And we'd also like to invite you to suggest other topics that you would like us to cover in future webinars. And one last thing to mention is, as we've mentioned our own software product Scalability a couple of times, if you're interested in SIL verification or you're looking for support with doing failure rate calculations, then a free trial of that software is available on request. So again, please just drop us an email and we'll arrange that for you.
I noticed that David has unmuted.
Yes.
I'm wondering if you have a question.
Yes, I do have a question. Sometimes in a certificate you find you don't find a lambda value, but directly a PFD average value. How do you have to handle with that? Can you insert it also like that in the scalability software then, or?
Right. Yes. Thank you. Very good and question. And actually, we should have mentioned that because that's such a common situation. So you can't insert it directly into the software. You need to convert it back into a lambda value. And there's guidance in the user guide given on how to do that. The problem there is, in order to back calculate the lambda, you need to make an assumption about the proof test coverage that was used to calculate the PFD average of the device. And usually the source of data that gives you the PFD average doesn't say anything about that. So then you're a bit stuck, and you have no choice but to assume 100% proof test coverage, which is over optimistic in some cases.
Yeah.
But so it's a straightforward calculation, a back calculation. I won't try and say what it is off the top of my head right now because I might make a mistake, but it is there in our user guide.
And is it wrong to play with the value to achieve the right PFD average calculated value then? So by trial and error? And you can play with the lambda value in the software and then see what's the result of the PFD average.
Sure. Yes, you could do it that way. Do it as a kind of a what if study. But the calculation is so straightforward. Honestly, the only reason I'm not saying it is because I'm doing it on the fly on the webinar, and just in case I make a mistake and mislead somebody into doing the wrong calculation, that's the only reason I'm not saying.
It's a very simple formula.
It is an extremely simple formula, but I just can't recall it off the top of my head at this moment. While we're talking, I'll see if I can find the place in our user guide that shows you exactly what the calculation is.
Thank you, Michael. Oh, sorry, David, do you have more?
Yes, I have one more question. You also said that the mean time to failure value and the lambda, it's the inverse of each other. But the mean time to failure, that's referring to the ISO 13849 norm, the machine directive. So it's that's then the way to convert a value related to the machine directive and to convert it into the SIL directive then.
Right. Yes. So the reason we mentioned the MTTF value there is because we just wanted people to see, roughly speaking, what's the mathematical relationship between lambda and MTTF. But you are absolutely right that MTTF, the term MTTF, is more typically used with machinery rather than with safety devices. And you're right that it's ISO 13849 terminology. So usually if you go out and buy, let's say, a shutdown valve or a pressure transmitter, it's not going to quote, well, it may quote the MTTF, but normally, as you say, the value that you actually get quoted in the documentation is either a lambda value or a PFD average value.
Yeah, but when I want to do a SIL calculation and there's no SIL certificate, but there is a certificate of the machinery, I could use that value MTTF to do a SIL calculation then, or?
Well, if that's all you've got, then that's what you're going to have to use. But I think we would want to raise the caution there again, the same as what Joe said about seizure and B10 values, that the MTTF value probably relates to equipment in continuous service, which is not subject to seizure failure modes, or less subject, shall we say, than a device that's normally in a standstill condition. And so it may be that the MTTF is calculated or is measured in a continuous application, which might not be valid for a demand mode application.
So that's high demand, low demand, what you mean then?
Right. Yes, that's what we mean. So you'd have to think about, well, is this going to potentially a problem for the type of device that I'm looking at here? And if it is, then you might need to rethink about whether that MTTF value is actually reasonable. What you could do is look at the order of magnitude of lambda that you actually get. I mean, if it says the MTTF is 10,000 or 100,000 years or something, and you run that through the calculation, you find it gives you a lambda value of 1 fit or something like that, then your eyebrows should be raised and you would be thinking, this doesn't look reasonable. It's not plausible to have such a low, except for electronic equipment. For example, the IO cards and the processor card in your logic solver, they could have that kind of dangerous failure rate of 1 fit, but not a mechanical device. That's not plausible, I think, in a demand mode application.
So I think if you're not sure about the particular device because you haven't had experience of seeing what would be a typical fit, an easy way to check would be to have a look at similar devices that have lambda values and make sure that your calculated lambda value is in the same order of magnitude.
Right.
Even if it isn't, if you can understand why it might be different, let's say there's for mechanical devices there's a much higher specified material in there, then you can say, okay, well, I can understand the difference there, that's fine. But as a first port of call, looking at similar devices will give you a sanity check too.
Yes.
Okay. Thank you.
And sanity check, I think that's a really good way of putting it, because that's what we're trying to do here. We're not trying to argue over the second and third decimal point. That's not important. The important thing is, have we got the right order of magnitude for the lambda value?
Yeah.
So if I thank you for the question, Michael, and also for your register of an interest in a webinar on FMEA. The question, Peter, is essentially the 10 million hours minimum that you said was a rule of thumb. Does it relate to an IEC or an ISO standard, which talks about what is statistically valid for field failure data?
Right. As far as I know, the 10 million number doesn't actually appear in the standard. Where I think it comes from, and this is where I'm going to show the depth of my ignorance of statistics here. I have to admit I'm out of my depth, but I think it's if you do know something about statistics and you do your calculation of how many hours do you need in order to come up with a value that has the, whatever the name of that statistical validity measure, the confidence measure, of whether it be 70% confidence, 90% confidence, something like that, you find that the answer that comes out. Joe, do you know more about this than I do? I know I'm out of my depth here, but
yes, it's something I'm familiar with, but not so familiar that I can pluck it out of thin air on the spot like this. But yes, absolutely. I think the better explanation is the one that you gave, Peter, which is to do with the number of failures, the significant number of failures that you've observed and the uncertainties arising from that. You could get you could start doing statistical analysis, look at confidence intervals, and there are actually two different statistical measures. One is related to your confidence intervals on your measure of your mean, because we've discussed means an awful lot here, but then another one is your confidence interval on your measure of the variability of the measure that you are considering, and really that's kind of like too complicated to consider. I think it's more it's much easier to discuss just the number of failures that you've observed, because that's something that's directly relatable. I'm not aware of any standards around in the area of safety systems and functional instrumented systems, which discusses what is the minimum requirement. However, tens of millions of hours are typically considered in the certificates, which are used to derive these failure data.
Right, that's it. So if you're looking at a SIL certified device, where somebody like Exeter or TUV has done the certification exercise, then part of the exercise is to look at the amount of field failure data that's available across the industry for that particular device, and they will be looking at whether the number of hours compared with the number of failures that's been observed is statistically valid using standard statistical calculations. One thing that is mentioned explicitly in the standard 61511 at least, and also 61508, is it does impose a lower limit on the confidence of that we have in the derived lambda values. For example, I seem to recall that the number 70% is mentioned in at least one place. So the outcome of that calculation, that confidence number, is we do have to know that. So that does at some point have to be evaluated.
Yes. Another question from Michael, Peter, a really pertinent question on the no effect failures. So the question is, if you needed to calculate a safe failure fraction manually, would you only include for dangerous and safe failures and exclude no effect failures?
Right. Yes, thank you. Very good question. The short answer is you do not include the no effect failures when you're calculating safe failure fraction. In case anyone doesn't know what safe failure fraction is, because we didn't actually mention it at all during today's webinar, the safe failure fraction is the fraction of the total lambda rate, which relates to failures that put you into the safe state. So in other words, to put it very simply, it's lambda s divided by lambda s plus lambda d. In the current versions of the standards, the no effect failures should be excluded from that calculation. But there is sometimes some confusion because an older version of 61508 standard included the no effect failures in that calculation. But that has now been removed in the second edition of the standard, which came out in 2010. So if we're working to the latest version, which by now we should be, then no effect failures should be excluded from the calculation.
There's a good reason for that, because what was found was that devices with a large number of no effect failures were warping the safe failure fraction measure.
Right.
And so it was almost in the interest of manufacturers to count as many no effect failures as possible to improve the apparent safety of their device.
Right, that's it. Actually, if you are interested in the background on this, we have a white paper available, which I think is free to download from our website on this very subject.
Okay. So you've seen on our final slide there, we have a webinar which is penciled in for Thursday the 17th of November on the operations and maintenance of safety instrumented systems. Please do join us. We've really appreciated your attendance here today. And Michael will have a look at doing an FMEA webinar as well.
Yes, absolutely. And also just to mention again that we do have our historical webinars from our previous series, which are all available on our YouTube channel. There's covering subjects like CHAZOP, which is Control Systems HAZOP, and SIL verification, fault tree analysis, and one or two others. So you just need to search for xSeriCon on YouTube and you'll find those. So I think that's all for today. Thank you very much for your participation. And we look forward to seeing you next time and hearing from you if you have any comments or questions. So thank you very much and have a great day. Bye-bye.